Hello, everyone. My name is Joe Delarose. I'm the program officer for Green Homes at LISC, Massachusetts. Fortunately, my video is having some issues this morning, so I'll just be on audio, but you'll have our wonderful speaker, Justin, on video and audio. So just so everybody knows, this session will be recorded. Slides and the recording of the webinar will be shared with attendees on our website page for the Energy Cohort. So I think this is a fun thing that we've been doing the last couple of times. If people want to put their names, organizations into the chat so we can see where people are coming from, that would be great. For this session, we're very excited to have Justin give a talk about electrification of domestic hot water systems. And it is a pretty content-heavy information with a lot of fascinating stuff. So we're gonna hold questions until the end of the presentation, and then we'll take them all together at the end. Yeah, I think with that, Justin, if you want to go to the next slide, just give a little overview. Perfect, thanks. Yeah, so just again, welcome all to the Energy Cohort. It's on the previous slide, Justin.
Oops. Okay.
Thank you. I think a lot of you know this already, but because a lot of you have attended past presentations, but we just want to give an intro for any folks who are joining for the first time. Energy Cohort is a learning networking collaboration group that we, in partnership with New Ecology and Massachusetts Association of Community Development Corporations, co-host to help affordable housing professionals such as yourselves to learn more about energy efficiency, decarbonization, resiliency, and resident health. Just a important note is that topics such as the one that is going to be covered today are all community sourced. So we get ideas from people in the field, such as yourself. So we always want to encourage folks to reach out if they have anything that they're seeing, any new topics that they'd like to learn about. I'm certainly excited to hear about this one. So just a final reminder for the people who've just joined us that the session will be recorded. So we'll be posting the recording and the slides onto our website. And with that, I'll pass it off to Justin.
Thanks, Joe. Good morning. Thanks for joining us. My name is Justin Iovenitti. I work with New Ecology. I'm in the Baltimore office. So we have 2 Mid-Atlantic offices in Wilmington, Delaware, and Baltimore. And I've been with the organization for close to 6 years now. I'm on the decarbonization team, so I'm really focused on existing buildings and trying to figure out how to make them more efficient, more comfortable, produce lower emissions, all the above. Here's a kind of brief table of contents for what we're going to go over today. It is a lot of content, so I'll try and go through somewhat quickly, but hope to leave plenty of time at the end for questions. So just to get started with some context, history of domestic hot water. It hasn't actually been since somewhat recently in terms of the entire scale of human existence that we've had readily available hot water in our homes, but it's something that's been desirable for a long time. You can see here some kind of an ancient image on the right. Going back as far as the Roman Empire, people were using solid fuel to heat hot water for different uses, especially bathing. So really kind of simple schematic about what we're talking about. In buildings, multifamily buildings, oftentimes we have some sort of water heating source. In this case, it's a heat pump. We've got a couple pumps. We have a storage tank where we're storing hot water. And ultimately that gets distributed through the building in piping to all the fixtures. And the fixtures is where we take advantage of that hot water through showering, bathing, cleaning, doing dishes, laundry, etc. It's important that our domestic hot water systems achieve a bunch of different things. They should be reliable, with minimum downtime and maintenance, hopefully. They should operate safely. This is really important. The water should not be too hot nor too cold. We need to minimize bacteria, make sure that flue gases are exhausted from the building if it's a fuel-fired system, and hopefully they're efficient. They reduce cost, reduce energy usage, and save water. So what fuels these systems? This is an example from the Northeast. You can see here this column. This is for all housing units as of 2020. So that includes single family, apartment, et cetera. Of the 22 million homes or housing units in the Northeast, about half of them use natural gas for domestic hot water. Overall, in the United States, about 48% of homes use natural gas to heat domestic hot water. You can see there's some other fuels used as well, propane, fuel oil, but it's primarily gas for the Northeast, and not quite a plurality, but a lot of homes in the United States use gas still. So we're primarily talking about electrification, and why is that? There's a number of different reasons. One is to comply with regulations in some parts of the country. You can see from this map, we either have building performance standards on the books or they're in the works. So that's true of Boston, Cambridge, I guess in some respects, the state as well. We deal with this in our area in DC. DC has a building performance standard, and the one for the state of Maryland is currently starting up right now. So we want to reduce energy usage, and electrifying these systems often helps with that. We'll get into that a little bit, but essentially, as we switch fossil fuel fired systems to electricity, depending on where we are in the United States, that's going to result in either a significant emissions reduction or perhaps small or not at all, no emissions reduction. And that really has to do with how clean the grid is. We have a number of different grids in the United States, and fortunately the New England one is one of the cleaner ones. So typically when we're doing this, we are reducing emissions as well. We want to improve air quality, indoor and out, health and safety as well. Improve resiliency. So perhaps there is some angle to switching over to electricity and being able to run some of these systems off battery backup. That's a question. It's not always the case, but it could be the case. Cheaper fuel costs. It probably doesn't seem that way. Certainly the electricity rates in Massachusetts are quite high now. I know the gas rates have recently experienced a fairly significant increase as well. So fuels are expensive. There have been studies that show that as fewer customers are using natural gas, that the rates for that fuel may rise more quickly than for electricity. But that's something that is posited. We don't know that for certain. In terms of timeline, the timeline for these upgrades might be dictated by different things. It may be the regulations that we just talked about. Oftentimes there are compliance cycles which last 5 to 6 years. So you may be forced to comply with those or pay a penalty. In the case of multifamily properties, you may be looking at a recapitalization every 15 years, which might be your chance to kind of chew off some larger projects. It might be hard to do so in between those recapitalization periods, or it could be failed equipment. Obviously, if we don't have a choice, we have to provide domestic hot water for these buildings. If that system fails, we're kind of, we must deal with that immediately, and something's got to be done. So it's kind of important to note that as we're making decisions about these systems today, the ramifications of that are going to go pretty far into the future. So just to talk about some electrification options, we're going to focus mainly on heat pumps, but I want to kind of introduce this a little bit. There's a lot of considerations when we're thinking about electrifying a building, even if it's just domestic hot water. What fuels are we talking about electrifying? Are the systems central or distributed? Who pays the utility costs? Is that something that the owner pays, resident pays? Is that potentially going to switch with the system change? Are there space constraints? So we'll talk about this in a little bit, but we've got equipment that might take up more space. We might need more space for storage tanks. Some of the equipment might go outside, whereas it's indoors now. Those are all things that need to be considered. And what systems are we going to evaluate? Which ones make sense for a given building? So here's one system type, electric resistance. It's typically, in terms of electric systems, it's often the cheapest cost, first cost. That's assuming that electrical service is adequate, which if it's an older building, it may not be. So that's something that is often like a primary topic of conversation. These units are not highly efficient, but they're typically more efficient than gas systems. In other words, they more of the fuel that's input into the water heating gets translated into actual hot water rather than being lost through flue gases, let's say. The storage and tankless options are generally equally efficient within a few percent, but tankless models obviously can save space. It's unusual to see central electric resistance in multifamily. It's more common to see these used within units or kind of distributed through the building. One reason for that is, if you're putting in-unit water heaters in, it can be challenging to vent the flue gases from those if they're gas, let's say. But with electric, that's not something you need to worry about. So we see these a lot in the Mid-Atlantic, actually, in individual apartments. The operating cost is typically going to be the highest of all the systems that we're going to speak about, and they're relatively slow to heat water. That's something called recovery rate. Solar thermal is basically, you have solar collectors typically on the roof. A fluid is circulated through those. It gets heated by the sun. This is fairly old technology, to be honest. It's been around for decades. There's typically a backup. If you have a few days consecutively without much or any sun, you're going to need something else to heat up your hot water. Could be electric, could be fuel, any number of options there. In that way, you kind of have two systems, right? You have your solar system and you've got your backup system, and you got to think about how are those sized. They do require regular maintenance, without which they won't work very well. We've seen this a lot. We've seen this system here is actually in Annapolis, Maryland. It wasn't working very well. It probably had a maintenance contract that had lapsed and was just in need of significant attention, but there was a fuel backup, so they probably didn't notice. Unless somebody was really paying attention to the fuel bills, they probably didn't realize the system wasn't working very well. The efficiency of these systems, I believe, has kind of plateaued, at least in my understanding, that's not the case for solar PV. Every year, solar PV is getting more and more efficient. The technology is still advancing significantly. So it may be the case that if you have limited roof space, it's better used with solar PV. And heat pumps. So this is kind of where we're going to focus today. This is a lot of the talk in the industry now is with heat pump water heating and heat pumps for heating and cooling, of course. Kind of two different styles here that we'll discuss. One is just a conventional tank, either we might call it integrated or standalone heat pump water heater. So this actually looks just like an electric water heater from this line down, and there's a heat pump component at the top. It's basically a fan, a coil, a compressor, very standard sort of equipment. The form factor is very familiar. It's maybe a little bit taller, but not significantly so. It uses conventional refrigerants similar to an air conditioning system. So there is some environmental impact there. On the other hand, we might have a split system. So a split system heat pump water heater would have two components. It would have an outdoor unit That's this thing here, which looks kind of like a mini split AC, and it has an indoor storage tank. So those things would be connected by water piping. This is a system that is sized perhaps for a single family home and a small apartment or a small apartment building, but it could be ganged together with multiple units to serve a larger building, or there are kind of larger scale options for heat pump water heaters as well. One nice thing, this is a system that uses CO2 as a refrigerant. So it works well, heats up fairly quickly, and most importantly, it's not a really bad greenhouse gas. Obviously, CO2 is a concern just because we have so much of it in the atmosphere, but it's not like some of the other refrigerants that have many times the effect of CO2 once they get into the atmosphere. We're not going to talk a lot about water-to-water heat pumps, but essentially, if you have a ground source heat pump like a geothermal, you might also one of the heat pumps in the system might be what we call water-to-water. So it might use the ground loop to heat domestic hot water. Sometimes it's called a desuperheater. So we have a little bit of a conversation about those in a moment, but for the most part, we're going to be talking about the air source heat pumps. All right, we're going to talk about some basics here of these systems. So everyone has a heat pump in their house. It's the refrigerator. Basically, the refrigerator takes heat and pumps it from inside the fridge or the freezer section and dumps it into your kitchen. So this thing is cooling. It's basically a heat pump in reverse, right? It's not trying to heat up the inside. It's trying to cool it down. And it's doing that by removing heat from the interior. It's just like an air source heat pump. If you're heating your home or a building with an air source heat pump, it's extracting heat from the outside air and dumping it inside the home or the building. Heat pumps are used for all kinds of purposes: space heating and cooling, water heating, appliances. We have heat pump dryers now, which are becoming more common, dehumidification, and industrial uses as well. This is something that's a little bit hard to wrap our heads around, but we're going to try. So whenever you have a heat pump, you think about kind of two sides of the system. You have a source side and a load side. The source side is where we're getting our heat from. So in an air source heat pump, we're typically getting it from the outdoor air. If we've got a heat pump water heater installed in a basement, we're getting that heat from the indoor air. If our source side is water, we're extracting heat from either a ground source, ground loop, like with geothermal, or perhaps sewer waste heat recovery is another way that we could heat from a water source. Since we're talking about domestic hot water, our load side, what we're actually heating the water for is a liquid. It's water. It's for the showering, the bathing, the cleaning, et cetera, that we discussed earlier. So in all these cases, we're inputting some electric into all these systems. Basically have a compressor. The compressor is run with electricity, but a lot of our input that eventually becomes hot water is thermal. And that, again, is the free energy that we take either from the air or from the water source. Some definitions. DHW, that's simply a shorthand for domestic hot water. HPWH, that's just heat pump water heater. You might see that written out, just shorthand. Coefficient of performance, that is basically how you might see a heat pump described in terms of its efficiency. It's really like a steady state metric. So it's a snapshot in time, how the unit is operating while it's running. For gas water heaters, especially the commercial variety, you see thermal efficiency. That's basically the same thing as coefficient of performance for heat pumps. Now, uniform energy factor is basically when DOE does their test on a residential scale water heater, it gets a UEF. If you go to Home Depot, you go to Lowe's, you see water heaters there, they will have a UEF. Higher is better. It's essentially a 24-hour test. So it will consider like the losses as the tank is just sitting there idle and, people aren't using the hot water. So that's kind of like a more holistic test. It's not a snapshot in time. It's over a 24-hour period. What we see those for efficiency of these systems, standard efficiency gas water heater, when you consider the losses through the tank and through the flue, it's about 60 to 70% efficient. In other words, we're burning, let's say we burn 100 units of natural gas, we're going to end up with 60 or 70 units of domestic hot water at the end. High efficiency condensing gas water heaters are 90 to 95% efficient. And then heat pumps, they can be anywhere from like 150 to 400% efficient. How is it that they're more than 100% efficient? It's what we looked at the previous, on the previous slide. We're only counting the electrical input. Basically, that's all I have to pay for. If I'm running a compressor and a heat pump water heater, I'm paying the utility company to do so. But the air I extract from the heat I extract from the air is free. So from that standpoint, we can have efficiencies greater than 100%. Some advantages of these systems. Efficiency, this is kind of what we just talked about. Here's an example just on the scale of a single apartment. If we consider this gray bar as how much load I have, so how much domestic hot water I might need over the course of a period of time. I'm showing 9.6 million BTUs. This is just like a general example. If I was heating that with a 95% efficient gas water heater, I would burn about 10.1 million BTUs of fuel to deliver that 9.6 million BTUs of hot water. But if I did that same amount of work with a heat pump water heater, I only am using 2.8 million BTUs of fuel. So they're significantly more efficient. This is just kind of like a visual to reiterate that. They will, if it's an indoor or outdoor heat pump water heater, will work more efficiently when installed in warmer spaces. So that's something that does come into play. If we're installing it in an unconditioned basement, it may not reach the level of performance that it would be rated for, but it still would be significantly higher than gas. Likewise, if we're talking about a split system heat pump water heater that has an outdoor and an indoor unit, that's going to be more efficient in a warmer climate than it is in a colder climate. Another advantage, no combustion on site. So occasionally, we run into dangerous conditions on site. This is a picture I took in January. This is a natural gas-fired domestic hot water heater. We can see that the foam insulation is melted here. It's melted because the flue gases are not exhausting out of the flue properly. They're spilling back into the basement of this multifamily property. And that's dangerous for many reasons, especially because flue gases can contain carbon monoxide. And carbon monoxide is deadly. It's odorless, and that's why we have carbon monoxide detectors in our home. Unfortunately, this building did not, but that's something we're working on. Another thing, no risk of explosions with electric systems. I mean, we have heard in the news of, unfortunate circumstances. It's happened in Massachusetts. It's happened in Maryland. Occasionally, there's a large gas leak and an explosion can happen. Also, these systems produce emissions. Anytime you're burning fuels, there's particulate that is emitted in the air. We breathe that in. It's not healthy. So there's, kind of all kinds of health impacts associated with burning fuels. Indoor air quality. So natural gas systems are inherently very leaky. The EPA says about 1 to 3% of the gas that's produced is lost through leaks. Who knows? It feels like every time they do one of these studies, they increase that percentage. So perhaps it's higher than that. Now, methane is the primary component in natural gas, but there are other hazardous chemicals as well, which are cancer causing. So if we have a small leak in a home, you might not notice it. It's not going to be something that is going to, you're not going to have an explosion or anything like that. But over time, you are breathing those chemicals. It's unhealthy. It can lead to asthma in some cases. We're just learning that about gas ranges. It's a major contributor to childhood asthma. So getting these systems out is going to improve indoor air quality. And then electrification, we see like kind of a broader switch towards electrifying systems. As we move forward, as the grid gets cleaner, we expect emissions to decrease, again, varying from region to region. It's very hard to read the units here. It's not super important, but this is for the New England grid. This is from an NREL tool. And this is basically, we're here in 2025. The units is kilograms per megawatt hour of electricity produced. We're way up here. By the time we reach 2050, the emissions from the grid should be about 1/6 of what they are today. So as we're reducing emissions by installing these systems, it's only going that picture is only going to improve as the grid gets cleaner and cleaner. Incentives. So in some cases, there are incentives that are available for these systems in a way that you really don't see much anymore for gas or other fuel-fired systems. With the Inflation Reduction Act, I don't really have a sense of how or when these might be available, just because of the steps the administration has taken to kind of thwart some of these programs. But we anticipated that some of these programs, actually some are alive already, like New York State is one example. We expected to see some of these launch this year. There's a homes and a here and a her program. These were the tentative numbers, but again, we'll just have to wait and see on that. Mass Save has some smaller incentives that are available. The LEAN program in Massachusetts, we'll see a couple case studies in a little bit, have a couple different programs that are available to multifamily properties that can certainly go a long way towards helping to shoulder the cost for these systems. Some design considerations. So these are the things we need to think about when recommending or suggesting these systems. Electrical capacity we talked about previously. So if you've got standard efficiency gas right now, you probably that water heater probably has no existing electrical circuit. If you've got a high efficiency gas system or a power vented unit, you probably have a 15 amp circuit to run the electronics or the blower for that system. But with heat pump water heaters, we are definitely going to need some form of electrical circuitry there. There are options for small heat pump water heaters at 120 volts, and that can work with just a 15 amp circuit. The downside is they're fairly slow to heat up water. So you really need to think about the capacity that you're providing. If you're going from a 40 gallon, you might need to upsize to 50 gallon just to make sure the residents aren't running out with their kind of standard habits. Now, larger heat pump water heaters are generally 240 volt, perhaps a 30 amp circuit. That's, again, you probably don't have that existing if you're working off of a gas system, but it's something that in some cases will be available in the building. In other cases, might have to run a new circuit, may in some cases have to upgrade service to the building, especially if all your systems right now that could be gas, let's say, are gas, then you may not have electrical capacity to upgrade the water heaters to heat pump. The location of the systems. So these standalone units get installed inside. They do take heat from that indoor air and discharge cool air. So if it's in a basement, probably that's not going to be an issue. If it's in a closet with a louvered door next to a bedroom, that could be a problem. The good news is this helps in the summer. You're going to reduce your cooling load, but it hurts in the winter. Essentially, you're stripping some of the heat from the heating system to heat your hot water. So that might have to be factored into the load on the heating system, especially if that is if that's going to be new as well. The good news is most heating systems are wildly oversized, so if you have an existing system, it probably doesn't matter. These units dehumidify while they're operating, so it is a great match for basements. It's kind of a nice side effect. In small spaces or closets, the lack of free air might require ducting. In other words, if you're trying to install it in a small space, there might not be enough heat in the air within that space. you might have to pull some air from elsewhere in the building or the apartment. These split system types have an indoor and outdoor unit, as we mentioned. The piping needs to be protected from freezing at all times because it is exposed to the elements. You might need additional space on the roof as well. Recovery rate is simply like how fast we can heat water. So gas systems are definitely kind of the champ here. So gas systems often don't rely on a lot of storage because they can heat water quickly. Electric storage are generally pretty slow. Hybrid heat pumps and CO2 heat pumps are similar to electric storage. In some cases, they can be a bit quicker. But oftentimes, when we have these electric systems, we're relying on a bit more storage to offset the slower recovery rate. I also want to note that for heat pump water heaters, the recovery rate is often tied to how warm it is. So especially true for the hybrid units, the standalone units that get installed inside. If it's quite cold inside, let's say it's the middle of the winter and the basement's cold, it's going to take longer to heat up water. Whereas if it's kind of a warmer month, it might be quicker. Gas and other fossil fuels don't really have that restriction. We don't have to think about seasonality because the fuel is always going to provide the same amount of BTUs no matter what the ambient temperature is. Storage space and structure. So again, this kind of goes back to what we just discussed, where when you have systems that heat water up more slowly, they're going to require additional storage most likely. This is a sizing curve that we might get from a tool to size heat pump water heaters. Basically, I can pick a point anywhere on the right side of this line, and I will be okay for this small building. This is like a 12-unit building. So what does that mean? On the vertical axis, we have the heating capacity of the heat pump water heater. Basically, how large the heat pump water heater is, or how many units I'm supplying. And down here, we have the primary storage. So how many gallons am I storing? So if I go up here, I see I might have a 50,000 BTU water heater and 160 gallons of water. That will satisfy the load for this building. But let's say I don't have room for that many outdoor units. If this is a split system, I want to reduce the number of outdoor units and I want to increase the amount of storage. I can go down here. I can size the unit for 40,000 BTU heat pump with 240 gallons of storage, and I will still satisfy the load. It's just going to do it relying on a bit more storage and a little less recovery rate. Anywhere in this section is going to be adequate. Structure is also sometimes a concern. If you're talking about adding very large storage tanks that you didn't have previously, there might be some structural ramifications. Noise. So the compressor in a heat pump water heater runs when heating is needed, just like a refrigerator. It emits some noise. If it's located kind of remotely, it's probably not going to be a concern. But if it is near, let's say, a bedroom, that might be objectionable to some people. Condensate, typically not a big deal, but we are blowing air across a coil for these units that are installed indoors. It is producing condensate. You see this white piping here that just drains the condensate, similar to your air conditioner in the summertime when you see it dripping. It's typically not a huge concern, but something to think about. In maintenance, so there are some maintenance requirements for these systems. The indoor units have a washable air filter that needs to be cleaned fairly infrequently, unless it's like a real dusty space. So that's something that does need to be done, but is relatively minor. Condensate lines and pumps should be checked and flushed from time to time. Outdoor units, may need coil cleaning every so often, just like an AC would, since they're exposed to the elements. Freeze protection systems, again, if we have piping that runs outdoors, we don't want that freezing. It could be really bad. So you want to make sure those are working properly periodically. Refrigerant and leakage. So all refrigerant circuits will leak eventually. That goes for air conditioners, heat pumps, refrigerators, etc. Refrigerant leakage, unfortunately, has very negative global warming impact. So our typical air conditioning and heat pump units right now are transitioning away from R410A because of the high global warming potential of that gas. It has an effect like 2,000 times what CO2 does once it gets in the atmosphere. So it's a pretty bad greenhouse gas. Some heat pump water heaters use R134A. So while it's better than R410A, it's still very high, 1,400 global warming potential. We're starting to see a lot of new heat pumps using R32. The new restrictions on refrigerant require that I think they're below 700 GWP, somewhere in that neighborhood. So any heat pumps that are installed like after next year will need to comply with that lower GWP. So we'll start to see a lot of R32 and R454B, which are both around the 600 number. And then R744, that's just carbon dioxide. That's what we call carbon dioxide as a refrigerant. It has a GWP of 1. That's because when we measure the impact of greenhouse gases on global warming, we compare it to CO2, the equivalent in CO2. Now, I do want to reiterate that methane is a really bad greenhouse gas. So as we have, when we have natural gas systems installed, a big portion of their global warming impact is due to leakage and that methane hanging around in the atmosphere for decades. So while the GWP of that is somewhat lower, it's 25, measured on, I think, a 100-year time scale, we're talking about massive amounts that is in the atmosphere. So that's really kind of detrimental as well. Factory installed refrigerant circuits leak less. If you're field installing refrigerant, that is more prone to leakage. Financial considerations. So equipment costs, the first cost of heat pump water heaters can be significantly more than comparable gas plants. This is just a really broad brush kind of rule of thumb, but a new gas plant in a multifamily building might cost $1,500 per apartment. A heat pump plant could cost 2 to 3 times that much upfront. Incentives may offset some of this cost, of course. Likewise, if you're upgrading these systems to avoid like building performance standard compliance or non-compliance penalty, that obviously would be considered as well. Perhaps installation costs may come down as contractors gain familiarity with the systems. That's kind of a hope rather than a guarantee. But some of these systems, especially the split systems using CO2, while they've been common in other countries, they're fairly new here in the United States. Now, in new buildings, not bringing gas service to the building, if you've decided on an all-electric building, that can be a significant cost savings. Controlling costs, so sizing. Gas water heaters are relatively inexpensive with respect to their capacity. So engineers or contractors, there's not a large penalty to oversize, right? They might be encouraged or incentivized to actually add another heater or upsize the heater to the next size. And you might not notice that much in kind of like your bill, let's say. With heat pump water heaters, again, the equipment's more expensive. It generally works better if it's right sized, not oversized. So we definitely want to focus on how we can right size the equipment. This can, as I said, improve the performance as well. So don't rely on rules of thumb or replacing like with like, because the system, if you have an old building, if you have a system installed there now, it's probably oversized. This is an example of a monitoring project that we had recently where we monitored domestic hot water usage for 2 weeks in a multifamily building. And this just shows the usage by hour of the day. So you can see overnight, like 3, 4 a.m., there's virtually no usage. And for this particular building, it kind of peaked in the late afternoon, early evening. So by doing that, we can understand exactly what the load is and right size the equipment. Another way to control costs is to reduce the load, how much hot water we need to provide. We can do that through low flow fixtures, drain water heat recovery, more efficient distribution, so less losses through the piping if they're smaller and well insulated, and controlling the recirculation loop in the building as well. What's the cost to operate for these different systems? So I've got one example here on the left with commercial rates for Massachusetts, one on the example of residential rates on the right. Residential rates are much higher, but you can see like overall, comparatively, the systems are in relation to each other, they're similar. So electric resistance is going to be the highest cost to operate. This is based on a single apartment using 63 gallons of domestic hot water per day. And, that varies with the number of bedrooms, the number of occupants, but this would be like a multi-occupant scenario. Gas storage and gas condensing, heat pump water heater, if they're operating kind of as they should, are going to be somewhat on par. Gas condensing is the lowest cost to operate based on the current fuel rates. So again, this is based on how much per BTU electricity is relative to gas. So while the heat pump water heater is the more efficient, it's using the less energy, the least amount of energy, because of the cost per BTU of electricity is a bit higher than gas. It's going to cost a little bit more to operate. And then finally, just a couple brief case studies, and then we'll get into some questions. Case study number one, this is a 13-story affordable building in Arlington. These are 132 one-bedroom units. So the occupants, it's kind of low occupancy, basically one per unit. This particular building was using electric resistance hot water heating. We monitored the hot water consumption over a period of time, and it was on the lower end of the scale. So this particular building was outfitted with 10 Sanco heat pump water heaters. You see 4 of them here, 1, 2, 3, 4. These are CO2 split systems, as we've kind of discussed a few times. There's 1,000 gallons of storage. There's also a 120-gallon swing tank. This installed cost was around $250,000. This actually was, both of these case studies were through the LEAN program. So actually the cost to the owner was 0, because these two properties qualified based on the number of units and the average AMI for the residents. A similar fuel-fired system would likely cost $1,000 to $2,000 per apartment. You can see this came out at around $1,900. This was, I think, a couple years ago. So the pricing is a little bit older. Now, this second example has a much higher cost per unit. So this is in Sharon, Mass. It's a 2-story unit, 99 one-bedroom apartments. The install cost here was $395,000, close to $4,000 per apartment. So again, when we were discussing the first cost being perhaps 2 to 3 times what it would be for a comparable gas system, here's an example that shows that. This particular property again uses the Sanco heat pump water heaters, the split systems. This had slightly higher consumption, so it's got, let's see, 12 units that are installed. Here we see 8 of them. They're kind of ganged together. This unit was previously, this apartment property was previously using propane to heat the domestic hot water. And now we switch it to the heat pumps. So they're off of that very expensive fuel. So I expect the cost savings here to be good. This is very recent data that we pulled within the last week of how the systems are operating. This blue line is showing one of the buildings here, and the COP, basically the coefficient of performance at different outdoor air temperatures. So you can see as the outdoor air temperature goes up, our COP goes up. Unfortunately, it's still, the orange line is the COP that we expect from the manufacturer data for these systems. And we're still trying to work with the manufacturer and the controls to figure out why it's not achieving the rated efficiency. So here's some references. Some of these things we've discussed, some are new, but obviously you'll have the slides, so you don't have to jot these down. I think we can now see, Joe, I don't know if you want to open up for questions if they're in the chat, or if
Sure.
you want to.
Yeah. Thanks so much, Justin.
Sure thing.
I think we had two questions in the chat earlier. So first, Caitlin, about an earlier slide. I think it was related to, it might have been related to rate of recovery or
Okay,
efficiency,
got it.
and asking where electric resistance would fall. It was a couple slides back, I think.
Let's see if I can find that one.
I think it was
Could it
slide
be
20.
around 20?
I think so.
Okay, so this, yeah, for the efficiency
Caitlin, let
example,
us know
if
if that's
this,
not right. Yeah,
is this right or not?
That's correct. Thank you.
great.
Okay, good. If we showed electric resistance on here, it would be, let's see, it would be very similar to the orange bar, just in terms of the primary energy used. The reason being, this condensing gas water heater example is 95% efficient. A heat pump, I'm sorry, electric resistance water heater, they're typically around 0.90, 0.93, something like that. So very similar in terms of, again, the primary energy used. Obviously, the cost would be much higher than the gas example, but if we're strictly talking about site energy, that's where we would be.
Another question we had, sort of touched on some case studies at the end, but
Yes.
Jens asked practical examples for split heat pump water heaters, specifically in glycol with an additional heat exchanger and circulator in the building, freeze pump with battery backup.
Yeah. So let's see. So this type of, this is a split system. I think what we're talking about there is a larger scale CO2 based heat pump water heater. There's some manufacturers. Mitsubishi is one that makes those systems. It's very similar to these systems we see here. There's kind of two primary differences. One is they don't, you can't run potable water through them. So that's why you have the heat exchanger. Basically, you have two sides of a heat exchanger. You've got kind of the outdoor unit side that might use glycol because it is exposed to the elements. You might use glycol, so you don't need to worry about heat tracing the pipes and keeping them from freezing. And then you have the indoor side, like basically the water storage, the hot water storage side on the other side of the heat exchanger. So technologically, I think they're very similar to the system we see here. They're just, you would need fewer units per project. Basically, the scale of those is on, I think there are maybe like 4 or 5 times the generation of one of these Sanco units. I've not personally worked on a building that has those installed, so I don't have an example here. We could probably find one. Are there other questions about that system that I
Do you
can answer?
typically, excuse me, Justin, this is Jens.
Yeah.
So
Yeah.
do you typically see it installed with the auto loop being a glycol? Or what do you typically see for these, like, for that section?
Yeah, I couldn't say honestly, because I just don't have enough experience with them, but I believe it could be glycol or it could be water that, again, you have some sort of freeze protection system that is probably going to be on emergency power so that, there's no downtime whatsoever. I guess the glycol would a little bit inhibit your heat exchange. That's kind of one of the negatives of using glycol, but some people might opt for that just because you don't have to worry about the freezing as much. And those
Okay.
systems.
So in your example here, you don't remember what you guys did for that?
This is so there's no heat exchanger here. So the water that will ultimately go out to the fixtures goes through these heat pumps. So these units, the piping here is all heat traced.
Okay, thank you.
Yeah. So you can kind of see, let's see if I can get my pointer. You can kind of see here, supply and return piping that is insulated with some pipe insulation. That's all heat traced. That's actually one of the things we're struggling with. It seems that the the heat trace is running quite a bit, maybe more than it needs to, and that might be one of the reasons why the COP that we see here is a bit lower than anticipated.
Thank you.
Yep.
We have a question about if you could speak to how wastewater energy recovery could work with the systems you're describing to make them more efficient.
Yes. All right. So there's kind of a couple different approaches. So there's a couple good examples actually in DC of sewer waste heat recovery. So in some cases, what they've done is we actually looked at this from one of our projects and ultimately just stuck with, I think we'll stick with a heat pump water heater like we see on the screen here. But essentially, if the sewer is a source of heat, the heat is fairly consistent through the year, and you might be able to tap into a sewer depending on where you are, what the utilities are nearby, what the size of that sewer is, and basically pull some of the sewer waste into your building into a specialized kind of heat pump that can extract the heat from it. And then basically you kind of return it to the sewer just at a lower temperature. So that could be done again on the scale of the municipal sewer, or it could be done on the scale of your building. So you're just capturing the heat from the sanitary waste in your building. Obviously, you're not going to have as much of it in that case. Like if you're looking to serve the entire load of the building, that might not be possible. Now, another thing that we talked about is drain water heat recovery. Let me go back to that. Oh, wait, I think I went too far. Hold on a second. So drain water heat recovery extracts heat from the sanitary lines in the building. So see the photo here. This is basically what they've done. These are, PVC sanitary lines. This is a new construction building, and they're changed over to this copper pipe here with another pipe that's wound around it. So as the waste goes out, it kind of clings to the sidewall of the pipe. And anytime there's a call for hot water, this actually is running the cold water through the outside of the pipe, heating up that cold water. Because every time, let's say you're taking a shower, you're typically mixing hot and cold water. Well, the warmer the cold water is, the less hot water you need. So it's kind of like balancing that mixed flow at your fixture. So that's another way. It's not really sewer. I guess it could be considered sewer waste heat recovery, but usually called drain water heat recovery.
Great overview, Justin. I think next Lauren had a question about the role of swing tanks and the best practice for design of that component of the system.
Yes. So when you have a CO2-based system, they're what we call single pass. In other words, the water that's getting heated up just travels one time through the heat exchanger. That's in contrast to one of the standalone interior kind of integrated heat pump water heaters. Those are what we call multi-pass. The water needs to go through the heat exchanger several times to heat up. It's gaining like a few degrees each time it goes through, and ultimately it will get up to that storage temperature that we desire. The CO2 units actually need very cold water because they have a lift of like 90 or 100 degrees. So they want a very cold water source, and they're then taking that up. Let's say it's 45-degree incoming water. They're going to take it up to 140 degrees through one pass of the heat exchanger. The swing tank is there to deal with the recirculation loop. So in a large building, you have a recirculation loop that keeps the water fixtures primed with hot water, so you don't have to wait forever and waste a bunch of water while you're waiting for the tap to get hot. Now that recirc loop might come back and only need, like it might come back at 100, 105 degrees, 110 degrees. So it only needs to be warmed up a few degrees, and we can't do that with a CO2 heat pump water heater. So we need a different type of what they call swing tank. It could be electric resistance. It could be a standalone heat pump water heater that's multi-pass. So that's what that system does. And again, that's another thing where some of the systems that we're monitoring now, we're having some control issues that we're trying to get to the bottom of, and hopefully, will not be like a detriment to the overall system performance.
Great. I think we only have time for like 2 more questions. What would make, I think you touched on this a little bit throughout the presentation, but what would make electric heat pumps, water heaters insufficient for an older building? What are specific obstacles?
I would say, the electrical capacity is probably the primary one. If you do have real old electrical infrastructure, I mean, honestly, like there might come a time when it needs to be replaced or upgraded no matter what, right? I mean, all systems have a finite life, and at some point your load centers, your circuits, your receptacles, et cetera, they're probably going to need to be replaced. But if for some reason you're unable to to provide adequate electrical capacity to the building, that would be something I think where it would be hard to make that work. There are things you can do with sharing circuits between systems that might help you out. So if you have loads that don't need to be simultaneous, you can share circuits and work within a smaller amperage like service. So one example of something that might, like a circuit that might be shared, if you had like a clothes dryer that was electric, or and a car charger, you might have to live with, oh well, I can't do both of those simultaneously, or there might be some other loads that could be considered like non-simultaneous. So I think that's the biggest obstacle that comes to my mind. Obviously, like if space is really at a premium, that's another one that could be challenging if you need a lot of storage, like with a heat pump water heater system.
Excellent. I think we'll do just one more. Greg asked if you have a comment on a commonish design proposal where heat pump hot water heaters are proposed in an unconditioned basement with supplemental electric resistance space heating added solely for the purpose of supplying the heat pump with adequate ambient temperatures.
Yeah, so those indoor water heaters, the standalone units, they actually work down to a pretty low temperature. So those manufacturers, because they are designed to be installed inside, there's no defrost mode. So the coil, if it gets real cold, there could be ice or frost that forms on it, and then it won't work. So those units just automatically stop running the heat pump at around 40 or 37 degrees ambient. Now, above that, if you have a hybrid system that has a heat pump component and electric resistance component, I think that's probably going to operate just fine. It's just going to be running at a lower COP. So my guess is that the electric resistance backup heat is not going to run a lot because, again, the unit has electric resistance in it, and it's going to call on that. Most of these systems have different modes of operation. They have a heat pump mode where it only runs heat pump. They have a hybrid mode where it will try and figure out the patterns of the building and anticipate if it's going to run out of domestic hot water if it's only running the heat pump. So it'll bring on that electric resistance heater in the tank if it thinks it needs to. And again, it's going to run the heat pump down to like 40 degrees. So unless you see that basement being very, very cold, like if you have some information about how it's operating now in the wintertime, then I don't think the backup heat might be good to have, but I don't think it would run a lot.
Awesome. All right. Well, thank you so much, Justin. This was a information-packed presentation. We really appreciate it. If we didn't get to your question, we'll be circulating the slides and the recording, and Justin's email is in there, so you'll be able to reach out to him if you have any questions. But thanks to everybody for joining, and we'll let you get on with the rest of your mornings.
Thanks for having me.
Take care, everyone.
Thank you.